First of all, before I start the talk, we're a relatively small group today, and that's nice. So if there's any kind of questions or something like that, I'm more than happy to go into an interaction. Also, just before, Ferrocene is unusual in that space, a fully open source product, so it's also very easy for me to, if there's a question that isn't on the slides, to, for example, pinpoint it in the materials that I have. So first of all, quick introduction of me. Hello, I'm Florian. Some credibility in the Rust space. I'm doing Rust since 2013. I've trained Rust since 2015. And I've been part of the core and the community team of the Rust project until 2021. And I'm also one of the co-founders of the Rust Foundation, also until about 2021, when I left all that for the reason that if you own a business and you do, and you are part of the project leadership, and then you represent the project in the foundation, suddenly you're in conversations where everyone wants your three opinions. So you're talking the policy of the project and the policy of the foundation and the policy of your own company, and it just gets way easier. And I like working with my team. Huge thanks for pulling that off. Ferrous Systems does a lot of open source maintenance, training, custom development, all of these kind of things. The reason why I put this slide on is particularly because of the maintenance. We maintain a lot of crucial parts of the Rust environment. If you've ever used, for example, the IDE Rust Analyzer, we produce that, and we also are involved in, for example, C and C++ binding generators and things like that. Today, though, I would like to talk about one of our biggest projects, which is called Ferrocene, which is the qualification of the Rust compiler for high safety, and particularly a little bit about lessons learned, interesting aspects of that may be reusable in other aspects. So this is the eye of the talk, talking about like some of the thinking that may be transferred to other things much more than, okay, this is just a project wrap-up. So I need to quickly talk about what Ferrocene is. It is a Rust compiler qualified for critical settings. It is particularly a reusable tool chain. So because it's open source, you can take it, you can compile it yourself, you can check all of these things. It is a reconfigured downstream of Rust/Rust. So it's actually compatible with the Rust compiler by virtue of actually being the Rust compiler, plus additions, and I'll talk about the additions, but no code changes. And the other thing is it's the first qualification of a new programming language of that scope since years, to the point where the assessor was like, okay, this is something that we also need to read up on. And long story short, we've reached that certificate last October, and I'd like to talk about how we reached it. One thing that's notable, mentioned that now, the Ferrocene compiler is not a subset, so there's the whole compiler surface is actually qualified for safety. However, we do some changes in the sense of its compiler configuration. So it behaves differently than the upstream compiler by virtue, for example, we're using an LLVM with full assertions on, and we're using basically every setting that you can put to very paranoid during compilation is set to very paranoid. And the other thing that's very unusual is we're shipping, for the virtue of what our development processes allow, all versions of the Rust compiler. Some of you may know the Rust compiler releases every 6 weeks, and we are able to forward that to our customers. Not each and every of them has the tooth stamp. This is something that we're still checking, like how many of those will we actually ship with qualification material and with long-term support. However, the people who use it are in the interesting space where pretty often they don't need the qualification, so they're interested in getting free choice of compilers. Just the moment where they need the high safety compilers, they're okay if the version numbers are a little bit thinned out. As said, it's an open source tool, so for anyone who wants to read along, github.com/ferrocene/ferrocene. is the open source project. You can see all the rendered docs of the current main branch on the public docs, ferrocene.dev/main. So always we have a blog. And there's the first interesting thing. Ferrocene is an open source project. It does currently not accept any kind of contribution, for the reason that we haven't quite figured out yet how we can trust contributions to Ferrocene/Ferrocene. Will probably be some kind of agreements or something that we have to have with people. But because it is a downstream of the Rust compiler, if you want to change the Rust compiler, you can go to the Rust project and get that changed through, which I go into detail later, is also the easiest way for us to change the compiler. Actually go to our upstream and get the change through there, and then let it fall through to us. Also, this is a talk more about practices, not about safety standards. I'm not interested in, for the sake of this talk, to talk about specific sections of the ISO 26262 or IEC 6158, because it's not necessary. If it interests someone, there was a talk just a couple of weeks ago in London at Rust Nation by my colleague Pietro Albini, how Ferrous Systems qualified the Ferrocene compiler, which goes more into the assessments of what tool category the compiler falls into, it's the highest, and things like that, and how those calculations work. I've skipped this for a reason. If anyone's interested, I'm also more than happy to talk about that over a coffee outside. So, the good bits of safety, in my opinion, are about being very honest about hard questions. And the first hard question is the main Rust compiler, generally called rustc, trustable to use in critical settings? And no gut feelings allowed. Make a case, write it down, and keep that case alive. That's the general and broad goal of this whole exercise. So, first of all, and this is pretty obvious, the Rust compiler is not something that we have produced in-house. It is what is generally called SOUP, software of unknown pedigree. Although we are pretty often members of the Rust compiler team, that's a 300-person team, it is pretty hard to figure out like what is the actual state of the Rust compiler currently. So it is not in-house software, and that means procedures need to apply to figure out how we set up a good process to import this into our house. Pretty often that is done by just grabbing one copy, doing all the work and keeping it around. Like that has been an issue, particularly in the 90s. Someone forks the GCC, ports it to a certain hardware platform, does all the work on top of it, and then never updates it. We've done this kind of work actually for a customer, and the customer has immediately banned us from doing that. No forks. Okay. Do we have requirements? Do we actually know how the Rust compiler should behave where our users can identify divergences? That's the important bit. Are our users or customers, whatever you want to call them, able to just look at our material and say, hey, by the way, I think your tool is misbehaving? Can they identify that by themselves? Question number 3. We all know Rust is a pony or a unicorn, and the best thing ever, it cannot introduce any hazards. I wish that statement were true. It isn't. Question is, how can we introduce hazards? Do we have an assessment? Like, what can go wrong? How can I hold the Rust compiler wrong? Yeah. Are we aware of any known issues in the Rust compiler? If we become aware of new ones, how do we react? How do we make sure that we already shipped a compiler to a customer, they have used it to build an ECU, the car's on the road? How is there a chain we can deal with that? I'll be a little bit less focused on that because this is a pretty big organizational issue and pretty standard. You have a support channel to your customer. Quality assurance. Do we have quality metrics, and how do we assure them? How do we, will we be honest about our quality is dropping, our quality is improved? Can we make a tangible argument that those metrics are actually useful? And then development procedures in general. Are there procedures in place to catch potential problems? So let's start with assessing what's there. The first thing, and I was a little bit surprised, the first thing we did when we started the project proper, we called TÜV and said, can we have a gap analysis? And the response from TÜV was, how far out is your project? And we're like, within the first week, and they were surprised. If you have anything to do with assessors, they really like it. If you give them a call and say, hey, we started the project and we would really like to, we're currently selecting assessors, and the first thing to work with an assessor is usually a gap analysis, particularly on something big. The problem with assessors is assessors are not allowed to consult for the reason that that encumbers the relationship, but they are allowed to say, hey, this is my checklist, and I think the following boxes are not checked yet. Completely. So they give you the gaps in the checklist. That is the service they provide. So we did that, got a list of gaps. Was during the pandemic, that was an 8-hour phone call. Good and bad Zoom meeting. Good because of the info, bad because of... the following main gaps that were found. No structured quality management in the organization. It's not a big problem. We were founded in 2018, small consultancy, a couple of Rust people. That's usual for young companies. This is something we got a good advice. Hey, by the way, there's a standard for quality management. This is the ISO 9001. It's pretty low bar. There's people who help you in that. It's also actually very useful for young companies to at some point level up the organization. There's things in there like, do you actually have fiscal management? Do you see if you go broke or not? So, you can get that one by just getting that ISO 9001 certification. Also, one of the topics I'll move out of this talk, because that's for an MBA conference. No hazard assessment of the tools in use. That's the much bigger problem. No one has looked at the Rust compiler very thoroughly and made a good argument of like, these are things that are sketchy or non-sketchy or things like that. That's very normal for a free and open source software project because you have pull requests and code review and something like that, but you usually don't have a general idea of what the tool should actually do in a structured way. And the last one was no unified source of requirement. The Rust project has RFCs. All changes need to go through an RFC, and this actually goes way back until 2012. But they don't exist in a condensed form. So there's no way where you can go and say, like, how should the Rust compiler behave? So that's the initial broad assessment. We need to figure all of these things out. The first thing to conduct is some form of risk analysis. We chose HAZOP. We were working with a company that operates a lot in avionics, and HAZOP is quite common there. It is one of the methods of having a structured analysis of components and their interactions to find possible causes of error. The nice thing about compilers is they're pretty straightforward. Source code in, binary out, which means you end up with a very small list of components and their interactions are top to bottom. So for example, we have a syntax processor. Once that's done, that goes to LLVM-IR. And there's huge amounts of the Rust compiler between it, but nothing that the user can interfere with, and that's the important part. Is like, can I interfere with this process, and what's the potential interference? The linker, for example, is a much bigger problem because you can interfere with the linker. You can start passing it arguments, and it might change what the compiler gave you. And you can't read this. What falls out is a long table, these kind of things. The nice thing and the important thing here is there's a lot of green bits in here. And this is, to my knowledge, the first time we actually looked at the claims that Rust is doing, particularly on being, is it syntactically resilient? Can you feed it programs that do naughty stuff that look legal and things like that? And we had a gut feeling that this is actually true. It was a design goal of the Rust programming language to be hard to misuse. We've even run an experiment where there's the underhanded C contest, and we had a contest that was the underhanded Rust contest. No one found ways to be very underhanded with the Rust language. A lot of people found very good ways to be very underhanded to the dependency management. So a lot of people here asked me about, is cargo a bit of a, if you want to interfere with Rust, you interfere with its dependency management? That's pretty interesting. Yeah. So it's the conclusion. Warnings are on by default. The tooling moves towards failure very quick, so this code just doesn't compile. However, it is a large code base, and all steps may introduce errors without user interaction. That's obviously a problem, miscompilations and things like that. But there's very hard, there's not a big surface where users can misuse it, which doesn't say that you can make tools that are internally very broken, but very hard to misuse. They're just broken by themselves. So that's the important part here. We need to be very, very sure what that statement actually means. It just means it's pretty hard to feed it trivially wrong programs by accident. This is, people always put Rust a little bit on a pedestal. I think that comes more from, it comes out of a wave of programming languages where that was an important design goal. Swift has similar things. Zig is also among that flock of programming languages. Zig moves into some amounts of unsafety and potential misuses, but with cause. They've done different trade-offs. It's like there's a 2015, 2016 generation of programming languages that has had an eye on this. And the minimal conclusion out of that HAZOP analysis is, yep, that was what we had an eye on, and we succeeded in actually meeting that goal. The Rust project itself, and this is another thing to do in the early assessment, what are the software practices of the tool that we import? The most important thing here is when we start setting up a project that is a downstream in the open source sense of another project, their software development practices become parts of ours. Because either we need to mitigate against them or we can adopt them, but we can never disentangle from them. It's the important part here. The only opportunity would be to completely fork and set up a thing on our own. This is also not uncommon. GCC and Clang are used in safety quite a bit, and every piece of safety material I've seen on them goes precisely the same way and has a section on this is how LLVM is developed, and this is how this is a problem or a blessing for us. But particularly the Rust project by itself has thorough and described practices of automation, and we need to keep them in mind. We'll come back to that later. So, given that we've got a rough assessment of what can go wrong and not, just to be clear, the outcome of the HAZOP analysis is, if you go to public docs, ferrocene.dev, you can actually read up on them. I don't see much utility in getting very detailed here. So the first and foremost way on how we can improve things for our users, user information. Let's talk about problems. Particularly, if you go on our front page, we have a user manual and a safety manual. And the safety manual, also standard procedure, is actually declaring what parts of the compiler we have looked at and how, and that means they are the only ones you're allowed to use or how you should use the compiler. There's some pretty interesting ones. So first of all, Rust has multiple profiles. It has every 3 years a new language profile is released. 2015 is generally the 1.0 profile. 2018 is a common one, and 2021 is the one that we released in 2021. And we have only looked at the 2021 one because it's very common, and our target group will write new software. So let's go. We only support the compiler with reasonable optimization options. Rust heavily relies on optimization, so it's that. And then we actually start with, there are actually LLVM bugs that are exposed through the Rust compiler and that can be mitigated by passing certain kinds of linker flags or LLVM flags, and we indicate to our users, you need to use them, otherwise our safety guarantees don't work. This is the nice thing about that environment. Our users need to read our documentation and follow it. So it is actually an okay mitigation to say, hey, by the way, you need to use the compiler this way, or otherwise it's your fault, so we can forward these things to our users. That's a trade-off. Obviously, no one will use your tool at some point if you're saying, hey, by the way, it's all your fault if you're doing it wrong. But we can, for example, indicate, hey, for example, one thing that is become apparent in this that Rust didn't mitigate against, there are certain Cortex-R models, the processor, that have hardware bugs, and there's a linker mitigation. The only thing we can do is we can put into the safety manual, by the way, if these are the Cortex-Rs that you're shipping, you also need to pass the following linker flag. So this is called an exported constraint. You have been informed. I didn't know there's a linker for that before. I know it. So we can relay obligations to the user. And for example, Rust famously has a part of the language that is called unsafe. Safe Rust, and there's unsafe Rust. And we can guarantee the absence of memory violations in safe Rust. I'll come to the star in the next slide. Ensuring that the use of Rust's unsafe features does not violate the language rules is the obligation of the user. And we cannot do it any other way, because that's the contract that inherently comes out of the language. However, and this is a criticism that I have to my own old project, we need to spell that out. So this is actually the next project that we're going on, is like, how do we deal with this sentence? How do we make sure that users can pragmatically work with a sentence? Like, how, what is actually unsafe? What are things that you can do wrong in Rust inside of unsafe blocks? Because that's something that's currently more knowledge of like 500 people around this globe that do unsafe quite a bit, know the rules and know how the compiler works and have looked at the assembly output. The document on how to properly and write and view unsafe code is not written yet. Still, from the perspective of I'm a tool vendor, I have no other way of saying, by the way, this is where the safeties are off. You have been informed that the safeties are off. So what does a guarantee mean? We guarantee the following. We have a method in place to describe the guarantees of the compiler. We're slowly going down to, we need requirements, and we inform of divergences actively. It is fine if we diverge here. For example, there has recently been a project that was called CVERS, which exploits a type system bug to break the guarantees of the Rust borrow checker in a very niche case. It's very hard to trigger. That's the reason why it hasn't been fixed yet, because the fix would require a rewrite of the whole borrow checker for something that no one accidentally triggers anyways. However, we need to inform people that these patterns exist and where we know of them. That's the so-called management of known problems. So we do have a completely cataloged list of all of these things. May sound a little bit trivial, but this is a catalog of all upstream issues that we are aware of. So this, for example, describes that if you switch the symbol mangling of the Rust compiler off, it is possible to create multiple functions with the same name, which during linking phase does anything like uses the order of the linker and the behavior of the linker, so you may not call the right function. Mitigations, and we need to say, hey, what are the workarounds? How do you detect it? And what are the mitigations? And so and the reason why we have that is, now this is the list of known problems for the current compiler. If we become aware of a known problem in an older compiler, the thing we ship to the customer is, hey, by the way, here's an updated list of known problems for that compiler. You can choose any appropriate mitigation steps, including switching to a new compiler or asking for a fix. Safety critical customers prefer to be informed about the known issues before they ask for a fix, because first of all, they want to see if they're affected, and if they're not affected, they won't change the system. Thank you, there's a bug, but I'm not triggering it. Nice to know. Information is the game. Now, we've talked a lot about evaluations and all of these kind of things. So the next job is, how do we inform our customer what we did? So I talked about HAZOP and all of these kind of things. So what we have as the next part is we have plans, evaluation plans, and reports that come out of this. And we have a so-called qualification plan and a qualification report. In general, the plan writes down what we intend to do, and the report is what we did and what we found. The report is semi-automated. Okay, so now we figured all of these things out about the Rust compiler. Now, that's been a library exercise, in a way. Went through all the issues, did the HAZOP, we have an architecture diagram. So we need to retrofit a couple of things. So, I've asked this before, how should the Rust compiler actually behave? So, talked about how can we inject errors, but the question is, like, there's trivial errors, like, okay, you run this on a processor and it bursts in flames or something like that, but what is actually the intended behavior? And now we run into a problem. There's a body of 3,559 RFCs. Some of them are implemented, some are policy, some are failed, some are succeeded, some are active, currently half implemented, some of them are half implemented and then dropped. It also exists. We have something that's called the Rust reference. That is incomplete, very much. It's an effort of 1 to 2 individuals. There's the book about detailed behavior of the Rust compiler as shipped by the Rust project. That's called the Rustonomicon. People want to rename it. It's been since 5 years that they want to rename it, but we're done. It's also incomplete. And there's a test suite. But the question with the test suite is, it declares what is tested, like very concretely, the testers and the testers, but not why. Like, why is this test there? What does it actually cover? And all of these kind of things. So we need to figure out behavioral requirements. Behavioral requirements for a programming language is a language spec. And Rust famously has no spec. Yeah. The on a reasonable budget is the biggest problem here. The fast is also, well, we want to get done at some point. So one of my ongoing discussions for the last 2 years in the Rust environment, and this is something that I find much more understanding in older industries and the C and C++ environment, is specs and specs are two different things. Like whatever, like you need to define what your spec needs to be. We need a spec that describes what the user can expect as compiler behavior on the very compiler that we are shipping. So if we're shipping Rust 177, we need a spec how Rust 177 as shipped by us should work. And if it doesn't work like the spec, that's the tension point where they can say, I think your compiler is not doing what you're telling me. I think I found a bug. It does not need to be fit for writing an alternative Rust compiler at all. This is not the goal of it. Eventually, a good spec has the property of allowing to re-engineer the system. So there's a discussion in the Rust project that they are starting to write a specification. So they have to deal with that question. We have to deal with, we need to describe the behavior that a user can expect. And particularly here, Rust is pretty well known for its reference and for its reference validity checking. That is a compiler behavior. There's rules of how references behave. The language does not mandate how it's checked. That's a compiler detail. So that was actually a good thing that saved us a lot of work. We don't need this. we need to guarantee to the user the compiler has facilities in place that make sure that references are never invalid, can always be dereferenced, and all of these kind of things. There's around 16, 17 rules. We need to make sure that the tool upholds these rules. We don't need to describe how exactly does that. So we have a compiler spec, but not we have a tool spec, not a language spec here. And also, it does not need to claim to be some kind of language definition. That has actually been a huge problem in policy and description when we actually open sourced. And this, just to make clear, like this is not our version of we think Rust should behave like this. We know our tool behaves like this. That also means on divergence, it's very probable that the compiler is actually right. In the sense of this is how the tool that I'm currently shipping is behaving, and this is what the user should be informed of, rather than claiming some kind of compatibility. So it cannot be used for any kind of compatibility. You cannot say, and this is very much in the first paragraph of the spec, you cannot say GCCRS, for example, which is an alternative implementation of the Rust compiler, is not a proper implementation of the Rust compiler because it does not conform to the Ferrocene spec. It's not the goal of the specification. More of a political issue. And as I said before, we do at some point want this for the reason that I want Rust to move into a place where the language behavior is more detached from its actual implementation. It was just not a goal that we needed to do, and also something that I feel uncomfortable of a company that is within that environment, just pushing it in the community. That's a little bit of the problem there. And given that there's so many interpretations of a spec, this is also a discussion that you kind of want to move out of while you have to finish a project. But you can schedule some amount of that work. You still have a lot of writing to do. So we got a very good advisor there, who was actually one of the co-authors of the ADA spec. And the things we did was particularly set aside quite some amount of time for writing custom tooling, and also spending some time to choose what the tooling we are going to write this spec in actually is, and to use different tooling in different phases of the project. And that means including the readiness of, hey, we'll start with this tooling, and we'll write migration tooling to the next one at some point in the project. I come to what this means in practice. So essentially, the workflow was, we took the Rust reference, we just took the outline. This is probably most topics that we should cover, 20 chapters, something like that. So the problem of the Rust reference is not that it does not cover most of the subjects in Rust. The problem is that the chapters are incomplete. So we found that was a good outline to get started with. And we actually wrote everything in Google Docs. It's just way better for conversations, changes, proposals, and all of these kind of things. And then we converted that to restructured text and Sphinx. Because now you have better versioning, you can integrate it into Git, we can actually put the specification aside of the compiler into one Git repository, use it in the build runs and things like that. Shout out here. We actually evaluated restructured text against Markdown and ASCII-Doc. And found structured text to be strictly better. As much as Markdown doesn't work, it's too simplistic. Whenever you want to do anything special in Markdown, you need to reach for inliner HTML or a non-standard extension. ASCII-Doc, we found, is logically impossible to properly generate. It has ambiguities. So, and restructured text is a nice middle ground. It's a well-described language, but it has arbitrary elements, like described in the language, that you can hook into that are meant as extension points. And we're using that. That's what I meant. It's like, do take your time to pick the tooling. Everyone nowadays defaults to Markdown and then ends up in horrible Markdown hacks. And we need the people to do that. And I was, at the beginning, very much of the opinion I really, really need language experts. And to an amount, you do. One of our language experts was actually, I mentioned, we produce Rust Analyzer. The person who writes the Rust Analyzer implementation of the Rust language, which is essentially a compiler in itself. It's really good to have those people around. But much more, you want people that have the eagerness to write. Characters in a text file is much more of interest, and you want people with the eagerness to research. Because no one knows the whole of the programming of the Rust programming language, you need to research all of bits, and the researchy bit is much more important. Essentially, the spec was written by an experienced spec editor, an experienced researcher, and 2 students. And that's fine. The students did a huge amount of work. Particularly, it were students that came out of the Rust Analyzer project, or you pick someone out of the Rust project, but the seniority is not that much of the matter, rather than a good feeling on how clean the work was and how sure they are that the answers they got potentially out of other project members are actually what's actually fitting the semantics of the language. You can't hire spec writers off the job market. That's just such a niche job. So this is how it looked like. I had to turn down the resolution. These were built on a 4K screen. So this is the Google Docs, and this is in the end the rendered Sphinx output. The interesting thing here is this is a very specific flavor of Google Docs. So these yellow things are actually, this is a keyword, and then the exporter will try to figure out, hey, I have a glossary, where do I find these kind of things? So every line here is a bookmark. So we can actually bookmark every line of the spec. And this actually turns out very useful here. You can't see this in this resolution, but this is actually a number that addresses specifically that sentence in this part of the specification. So that's probably 20:4, something like that. That's the number, and we can directly address that. That's actually coming from the ADA spec, a little bit beefed up, like the ability to pinpoint every part of the spec using a computer, and we'll exploit that. Still, we at Google Docs format, we also managed to get the bookmarking script wrong at some point. It turns out deleting bookmarks on Google Docs, we have reported this bug has a quadratic complexity. So we had something that was deleting bookmarks for 2.5 days in the end to get one of the documents back up. So mistakes were made. It has been very useful to have people around who have a very good feeling for, this is actually the moment where I stop writing that document and I start writing a 20-line Python script. So this kind of like engineering discipline of backing off and writing a script can be really useful also in this kind of very structured text management. Yep. So that's the retrofitting part. We need to, like, essentially what we've done is we've collected 3,500 roughly documents and condensed them into, okay, what's actually the picture that comes out of it if we sum them up and if we throw out things. And that's a massive amount of work. That was about half of the project length. So, reuse. Now that we finally got behavioral requirements, how do we make sure that they are met? And interestingly, this is where a pretty weird thing in the Rust compiler comes to our help. The Rust compiler does have tests, and it has behavioral tests, because some may remember Rust was written within Mozilla Research. So for better or worse, those are browser engineers. It's a browser engineering organization. How are web browsers tested? There's a massive test suite that just goes test the UI of a web browser. And it happens to be that the test suite of the Rust compiler, the main folder is called UI. We test the UI in these things compile, these things don't compile. They give specifically this error message. So if you change an error message in the Rust compiler, you also need to change all the tests to update them, that the error message is now exactly this. So there's a high, there's high expectancies on the test quality, and that's something that actually, in the other way around, we need to retrofit all of the requirements. But on the other hand, we did not have to write many tests. What we needed to figure out was, what do the tests apply to? And this is where a hyperlinkable spec becomes very, very useful. So each of those items in the spec here are linkable. Sounds a little bit big. This is a 150 lines plugin for Sphinx. So if you want to reuse this, go to our GitHub. It's custom for us. Please fork it in this case. We don't give support for that, but that's the least magic thing. And the other thing that we did is we mapped those tests to the spec. So this, for example, is one of those compile fail tests. This is a syntax error. Let x is I size 3. What's missing is a semicolon between the type name and the actual value, the actual array length, sorry. And the exact error is to the right. Error expected is one of the following characters. And what we have below here is, this is called a trailer. Rust tests have a framework that allows them to be annotated, and usually using headers. We have asked the Rust team to also allow us to build trailers, and we put here, okay, this is a Ferrocene annotation. It goes to the section FLS, and then this kind of cryptic ID. And then below that, the title of that section, which is array types. Tests may cover multiple sections, so these annotations can be repeated if you have covering multiple sections. And yeah, come back to why this is a trailer, not a header, in a second. Does someone already have a hunch? No? Okay. And we've done this for all tests. And as I just mentioned, Rust has a lot of tests. So we needed to go through all the tests and all the test folders and annotate them. The saving grace here is the test suite is also well organized. So sometimes here's a folder that checks a specific language feature, so that we do allow that we're saying, hey, by the way, all tests below this folder are covering the following sections of the spec. Still, this is mind-numbing work for the first iteration. So the moment you have to do this for a test suite that has 5 figures of tests, here again, this is more a people management problem than anything else, and you really need to push through this. So our conclusion was we start early so that we can do it in slices. So we had people that would do this every Monday and not for a whole week, something like that. So on these kind of things, if you're already seeing the train of this very rote work coming down the line, it's very useful to say, okay, let's start it very early, so that we can have someone do that at a time. The other thing is, I mean, this is standard management psychology. On repeated tasks, humans get worse the longer they do them. So if you do this 5 days a week, the quality on Friday will be really terrible. So that's the other problem. We still need accuracy. And the goal here is relevant breakage. So we want to be able to see, hey, has the Rust project added tests? And if it has added them, which part of the spec do they apply to? Or did we add something to the spec that we haven't covered with tests yet? Or that we haven't found tests that cover it? That I didn't put on the slides, we actually had very good experience with most of the things we wrote down in the spec actually covered with a test, which was also very useful in research because we could see, okay, this is how the compiler should break. A lot of the tests in Rust are actually the so-called compile-fail tests, because if you have a language that should catch a lot of errors, there should be a lot of tests for errors being caught. But the important thing is, I think breakage is good, and working towards breakage is an important thing in software quality. in a predictable fashion. If your breakage is always all over the place, you have a quality problem. If your breakage is, by the way, a test has been removed, we need to figure out why it has been removed. That's the process working as intended. That's the part of we are not in control of what's happening upstream. So breakage is the way where we figure out our upstream has diverged from our expectations. Yeah, and talking about upstream, so we have a careful and mergeable project structure. This is why the annotations are trailers, because additions to files in Git merge cleanly, additions to the front of files don't. So the Rust compiler goes downstream, so we downstream the Rust compiler with annotated tests. If they change the test in some way and they test the test message or something like that, like the error message for the test that I've shown has changed, it changes the lines on top of it and it doesn't change the trailer. So we can just cleanly merge this. Come back to merges in a second. And we have some amount, we have very clear tracking for all of this. This is our so-called traceability matrix. This is the matrix that actually checks the status of this whole project. And this is the one from today, and you may see this tiny yellow dot. Again, resolution is a problem. This says on the field of macros, something has changed, and we are only tracking 86.67% of the tests. It seems like tests were added. Here, for example, we are saying this is actually fine because the only place where this needs to be at 100% is if we actually release the compiler. So we are allowing these numbers to drop for the reason that it makes it easier to later on to just get these changes together. Yeah.
Hello? Okay. So what do you have to do? So do you have to qualify, to map all the tests, or do you just want to reach the coverage that you've covered all the parts of the spec that you want?
It's a good question. Our interpretation is both ways. We want to know why the tests are there, because that is an indication of either we haven't established what those requirements, what is this test even there for? That might either be it's belonging to a requirement and it's just increasing coverage on a certain requirement. The other way around, or it might be, okay, there was a test added for a new language feature that we haven't covered in the requirements list yet. So that's the second option.
Okay, but so what happens if you find a test that you cannot map to any of your specification?
Yeah, we need to change the specification. Rust is an evolving language. My view on specifications is always specifications open up discussions. If it diverges, we need an engineer that looks at what's the divergence, why did it happen, do we need to change the spec? It does happen in the Rust project that sometimes things are introduced and not properly communicated, and we need to get that. It's pretty rare, but it's a 300-person project. Things slip through. So, yeah.
And does your mapping map back to the RFCs then, or is your document then the standalone?
It maps back to our specification, and we update the specification. So before every release, so if 177 or 178 comes out, we do one of those runs and figure out, do we have all tests mapped, and do we have all language changes changed? One thing to note, just because the Rust project releases every 6 weeks does not mean that the language changes every 6 weeks. It's actually becoming rarer and rarer. We have about 2 to 3 language changes every year. Yeah.
Thank you.
Thank you. Yep. Coverage. So now let's make a case out of this. So as said, we have this tracking from plans to reports. Plans are handwritten documents that document the ahead planning. of our verification work. Reports may be semi-automated and document the results of executing the plan. So the evaluation plan, for example, it communicates all the things I've been talking before. It says, okay, this is a qualification scope. We qualify by ISO 26262, 61508. There's a lot of work that we will have to do for them. 5.3, for example, determine tool impact and error detection level are something that ISO 262 mandates. This is a way of classifying how hazardous the tool could be, all of these kind of things. And the other part is the qualification plan. That's the actual interesting, or that's the more interesting plan, which is the plan for following our evaluation. So out of that evaluation come activities that we want to apply to certain parts of the system. And there you see, by the way, here's the history, for example, Rust project, contributing to upstream, and so on and so forth. How does our organization look like? So this is a holistic view on how the whole thing works. And we turn that into a qualification report. And this, as I said, is semi-automated. And for example, it says for ARMv8A bare metal, here are the test results, and here's a list of ignored tests, which shows which tests we did ignore. Now the question is, what tests do we ignore? For example, because it's ARMv8, tests that specifically test x86 are ignored, because they can't run it on ARM. So it's that kind of statements. But we do list for every test, why is that test ignored, and for each and every test we need to give an argument. And it needs to be a thorough argument. As I said, usually the argument is we are evaluating those tests on an ARMv8 machine. Same thing on the other way around, x86, 64, ignored tests would be ARM tests, things like that. Still, we need to be detailed there. So how do we make sure that this is in check? So that brings me to the most interesting bit, I think, is quality management. Up until now, that was mostly, okay, how do we establish the world that we have? The problem is, how do we make sure that it stays that way? The Rust compiler moves fast. We have 1,600 changes between releases every 6 weeks, and the Rust team does not shy away from massive internal refactorings, including taking the whole test suite, putting it on its head, introducing new intermediate layers into the compiler and all of these kind of things. Also comes out of an engineering culture that's very used to manage large code bases. But the important part here is it has a number of ways on how to deal with this. And the most important one is the not rocket science rule to software engineering, which actually Graydon Hoare, who invented the language, described more than a decade ago. And the rule is simple: automatically maintain a repository of code that always passes all tests. Problem solved. No, there's obviously something more beyond that. So first of all, that speed can have positive repercussions. The refactoring happiness means there's huge churn, and Rust has strong backwards compatibilities. I would like to highlight, if you enter discussions about this backwards compatibility of Rust, read RFC 1122 and 1105, because those are specifically the RFCs that declare what is actually part of backwards compatibility. A lot of backwards compatibility discussions in niche areas of Rust end at, oh, by the way, the 1122 has carve-outs, for example, for pointer behavior on FFI, because we knew that was not fully defined yet. So these are things where Rust, for example, has undefined behavior, which we declare what undefined behavior is in our safety material so that no one runs into these kind of things. But please be aware that these RFCs exist. But it has massive test coverage to assure behavioral backwards compatibility. That's where the large test suite comes out of. In practice, the Rust compiler does not change its behavior very much between nightly versions, despite these massive refactorings, precisely because of that interplay. If I have huge churn and do want to make large refactorings, I do need a very thorough behavioral coverage. That's very much playing into our hand. the upstream project already does a lot of things that we need to do. So just as an aside, there's a test suite called Crater, which tests the behavior of one compiler version and a patched compiler version against literally all crates on crates.io, plus a curated list of projects on GitHub. The list is curated because we cannot just, like, there's now so much Rust code out there that we need to restrain ourselves. That test suite runs for 3 days somewhere on Google Cloud. It then checks whether the test output of the first one is the same as the test output of the second one, byte by byte, figures out divergences, and if it diverged unexpectedly, will revert the patch. So, I mean, 3 days on Google Cloud is not that horrible against the price of an experienced compiler engineer, but still, that is a bit out of, Rust comes out of a culture where there's actually some amount of money available. Many open source projects come out of a culture where that is actually a problem. Rust comes out of a culture where automation is feasible, and so yeah. But how does the Rust project do the assurance there? And we have taken the same approach. We are actually using the same rule here. There's a tool called BORES-NG or merge trains. The important thing about BORES-NG is BORES is the build bot of the Rust project. NG is the next generation. It is discontinued because GitHub now has features like that as well. We cannot use the GitHub features yet because there's niche issues for very long compile runs, and the Rust compiler builds for an hour. However, so we maintain it ourselves. You will find equivalent tooling for your project if you want. This kind of, also one comment, this kind of tooling needs projects that have a certain kind of scale, particularly in contributions. For example, we used this on our website, it was terrible. So what it does, it maintains a queue of pull requests that are ready to be merged because they were reviewed. But it serializes them for testing, so only one of the changes runs at a time. It also automates all operations on the repository. No one uses Git or the GitHub buttons. I am not allowed to merge on main. Our infrastructure master is also not. It does all the important bookkeeping, for example, tracking who reviewed and who authored a change, and signals back status changes to GitHub. So this is how the flow looks like. Pietro Albini has said, well, these changes are okay, says BORES merge, then BORES says, hey, by the way, I'm waiting on my own automation. Then it says the build succeeded and merges the change. One interesting thing that it does what it does is it branches the main line, merges the patches on it, so it's on an off branch, does the testing there, and only if that branch checks green, it merges back into the main line. This is how you make sure that your main line always passes all tests. That also means a lot of people are in for clean Git history. The Rust project isn't, and we also aren't. We do merge commits. And most importantly, what it also inserts is not only the things that were merged, but also who reviewed them. Here, review was by Pietro Albini. The author was Wakefield. And the other way around, for the other patch, the reviewer was Wakefield, and the change was Pietro Albini. By the way, names are Lucas Weird, Pietro Albini, so good Git usage. We're using as much metadata that Git gives us. Merges are good because we see when changes were actually put in. And this is all done by the automation. Now the question is, why do we serialize all commits? Here's a problem. If we were to approach the problem, as I just mentioned, we branch out and we change the pull request. If we run in parallel, we might have a feature X and Y that both test green, but if you merge them together, the main branch is broken. This is unresolvable. We do actually need to serialize all changes. So changes committed, tested, merged, branched out again, next pull request. So BORES maintains this queue, so our engineers can put something in the queue runs overnight and reports them back whether there were problems. If this becomes too slow, what you can do, and which the Rust project does, you can say, hey, by the way, merge multiple small changes together and test them in one go. If everything still checks green, we're done. There's some subtlety to this. If someone's very interested in that kind of automation, there's a whole environment around this. It's also in our documentation. But that's the rocket science rule.
How many different platforms are you testing on, actually?
So on all of our supported platforms. So the Rust project and we as well have a labeling of a classification of targets. And the highest classification is tier 1, which is merges block, blocks merge, blocks release, and is tested. Tier 2 is build errors, block the merge, and block the release. Tier 3 is we're not even building that target. If you want to use that target, download the Rust compiler and compile it yourself. Just to guarantee, and the same thing we do for everything that is actually released to our customers. For the first, that was a screenshot from our first edition. That was really just ARMv8 and x86, Cortex-A, moving into Cortex-R and Cortex-M. These are all tested, and all of them are tested. So that green means all supported platforms are green by their test configuration. And that also means, for example, if we say we have tests and ignored tests, that also means ignored tests are only ignored with cause. Yeah.
Another question. So how do you test this? Do you have platforms where you have the hardware, of the correct hardware, or do you have simulators?
A mix. So here so Cortex-A's are now available as cloud platforms. So we're testing these. Cortex-R's and Cortex-M's are currently, so Cortex-M's we're looking at fast models mostly. Cortex-R, there's a cloud product by ARM currently that simulates an R core to the appropriate accuracy. The nice thing for us is essentially we only need to test the code generator. So we really only need to test the core. So no devices around it. So the simulation problem for us is far easier. TÜV accepts QEMU on a lot of platforms nowadays as being an accurate simulation of the core. Yeah. We do prefer simulation because it's easier to set up. Right. A few notes on the testing habit here. The Rust project, and by extension us, considers every test a release. So this will be uploaded to the artifact host under the current Git commit and things like that. That means if the Rust project releases, for example, Rust 177, all it does, it puts a label somewhere on S3 and says this release, by the way, was 177. The advantage of this is if we find a bug, we can actually run bisection because we can download each and every version of the compiler and can figure out where we actually introduced the bug automatically by running a test script against it. That tooling exists. What we've done is we've, for example, here's the traceability matrix. Again, sorry for the resolution. So this, for example, is running on releasing one of our branches. And so the testing and all of these things become part of our release process. This goes as far as if we do actually sign documents, because for qualification I need to sign, by the way, this document, by my knowledge and by the virtue of me rereading it closely is correct. We do that digitally. So we can even assure that if someone, for example, changes something on a branch that has been released as a qualified compiler, the signature will break. Again, work towards breakage. The documentation changes. Someone fiddled around with the documentation or the behavior of the compiler, my signature breaks. And no one can say, hey, by the way, I'm using I've used the safety manual. No. Still a pretty interesting concept that I have rarely see used. This kind of, we don't have any kind of release tests for play. We only have release builds. And that's it. Simplifies the thing. There's only one build flavor. And now that we have all this set up, how do we constantly re-ingest upstream? We are not we are not just following upstream what we're doing. We do actual merges. So we merge the upstream compiler and the current state into our compiler. We have the same history, plus eventually some mergeable side history. And that means it follows the same process. So if tests are breaking or certain things that we're looking out for breaking, the merge from upstream breaks, which means an engineer needs to look at it and figure out what broke and what happened. This is actually a quite frequent thing, either because of refactorings that don't merge well, or because we're testing different platforms. So upstream may accidentally introduce a bug on a platform that they haven't had. And this is quite useful because that means we have a follow-up of a couple of hours when we actually figure that out, that upstream broke something, and we can go back to upstream and tell them, hey, by the way, we've seen breakage here. And they know us, they're receptive for that. Yeah. So it gives us a pretty straightforward path to improvement. More tests, not only we need to add more test files, we find different ways of testing the compiler. We're currently looking at a way on how, for example, to ABI tests against common C compilers and things like that. But still, that's an extension of that process. We don't need to change the process. We can work on what do we do within that process. And this is something that you can expect someone who works with a Rust compiler to know, because that has actually been a process that has been in place in Mozilla since that repository was open sourced. Mozilla Research had the principle of if it can't be released, it isn't software. And radical statement. So it was essentially built out as this process existed with a very small compiler in the middle, and then we built out the compiler and the tooling around it and so on and so forth. But the process is is a decade old. That means people also have experience in how to handle both. Also, that means you can't just go and say, hey, this makes total sense. I'll introduce this into my team, and you frustrate them for the first. So do this slowly, please. Yeah, so our part is all of our work also becomes part of that process, and we don't want it to break, at least not in unexpected ways. As I said, we are allowing coverage drop-off, and we are allowing the spec not being followed up in between releases, just because that allows us to batch it. As long as the metric of tests are unchecked or there's gaps in the specification is accurate. Because then we can go and say every 2 weeks, someone looks at this and fills the gaps. But that's suddenly we're in the process thinking and not in the, oops, what happened here? Second one, stay close to upstream's development. Rust upstream already has strong software practices, and essentially we got an assessor to sign off on that this is actually a useful process in the safety critical world. And that's quite an achievement, taking the process of an open source project. Like there's this whole discussion about, can open source even be certified? And the general answer is, as always in engineering, it depends. If you happen to have an upstream that already has strong quality assurance policies and some amount of thinking about that, well, it's probably easier than if you don't. And we are in the lucky situation where it actually is, and where we are also employing, for example, the infrastructure team. All of this was also possible because we're employing the infrastructure team of the Rust project, and that was a deliberate hire. Now, finally, for the end of it, you've talked about, okay, Ferrocene is open source, can we qualify open source and all of these kind of things. The other thing that we really wanted to look at was, is open source in general actually fit for these kind of things? And the answer is actually a good yes. I've talked a lot about these things, but I would like to highlight the tools that we're using just in a quick overview. It's actually not that much. We're using reuse which is built by the FSFE, Free Software Foundation Europe, and it's a tool for license checking of complex and large code bases. It's a really, really good tool. Documentation, we're using Sphinx and we're using an extension of Sphinx. It's a really, really reliable workhorse, and I can only speak highly of it. Really adaptive maintainers. The thing we contributed is repeatable builds to Sphinx, so to building. And it was pretty niche. The search index that they were building was not repeatable, so it was not even a big patch, but we made sure that that works. We use Sigstore for the digital signatures that I talked about. Sigstore is a really nice implementation of you log in with your Active Directory or your Google Cloud into Sigstore, which is a project done by the Linux Foundation, and then it allows you to sign using a command line program. So it uses your actual credentials from your employer for your signatures. So you don't need to set up like a secondary KPI key management system. Talked enough about BorsNG. The star is here for BorsNG is discontinued. Please be aware of that, but that doesn't mean that the principle is discontinued. It's discontinued because there's most, like GitLab and GitHub and all of these have this idea now built in. So if you want to adopt it, I highly recommend checking that first. As I mentioned, BorsNG has certain facilities that we're still waiting for GitHub to implement, and when they're done, we're off. Cargo Dist is a really good tool done by a startup in Austin called ACCU, and they basically like, why are we always setting up our release processes again, like with release of binaries, MSIs, and all of these kind of things. So if you have a C or Rust program or something like that, they just detect, okay, here's the binary, and they wrap it in an MSI. Pretty niche thing to build a startup around, but something that someone always repeats. And in the end, Python and Bash. Is there software without Python and Bash? We've seen it yesterday. Python being the second most important language next to C++, and I'm pretty sure that's the same thing with Rust. Even as an old Rubyist, I have to yield that win. But the other thing, why are we using open source, and why are we building this thing as open source? It's more about relationships than about the licensing. It has been really, really useful for us that our licensing is the same as the Rust projects. That means there's not a lot that can go wrong, like not a lot of license checking, like it's all compatible. Sometimes the copyright header is wrong or something like that. We find that the companies that we talk to are much more flexible, want to get more flexible and creative around their tooling. I mean, we also have quite a lot of people around here that work on C++ compilers, integrating them into similar systems and things like that. And there's a reason why OEMs are walking around at ACCU and suddenly hire compiler engineers. And our relationships become more and more maintainer and user relationships. Also important, was that a lot of paperwork, or did we actually, like, were there quality improvements in the Rust compiler coming out of that? Quite a bit. Structured output for the build system. Before that, you would just have to parse strings and try to figure out what it was. So basically, the build system was built for being read in the console. Now we have structured output so that we can actually put it into material. Pin checksums of the Bootstrap compiler, so we made the bootstrapping a little bit more resilient. We particularly started a clarification of the licensing. There were some unclear parts. We're the only ones, the first ones who actually started running tests on bare metal. So your question, where are you actually running the tests on? I can say until last year, no one ever run the Rust compiler tests on an actual microcontroller. It's good that not too much broke, but things broke. Yeah, we had also quite a lot of things around like tests and long file systems. We're finding issues, like a lot of small detailed issues, and we're working on targets x86 and ARM v8a are not necessarily targets that are underused in Rust. Those are very common targets, and we're still finding small bugs. So in general, I would not say this is a quality issue of the Rust compiler. because most of the people don't trigger this bug, or they're in an environment where they can just redeploy. If you're AWS, it's like, yep, broke, I'll redeploy. Still, I think it's important to note this tangible outcomes coming out of that. Although it feels a little bit like cleaning in the corners are important. Now I don't know what's up with the slides. It seems to be that I accidentally, yeah, that's what I want. Did some slide modification. So, general observations and experiences. Having done a lot of that thinking, it brings you to higher level conclusions about the environment that you're working in. And that means, and that's what I would like to invite everyone who particularly adopts Rust in those spaces, just be aware what the environment gives you, and look at the things that it might create or not. Just because and particularly just because a tool is well vetted, doesn't mean that everything's magically safe. For example, Rust has a constrained plugin system called procedural macros. It can generate code from the template of structures. And what it does, it looks at the AST of the structure and allows you to create additional code. Well, so you vetted whether that plugin API works. It's one function that works. It's really easy to vet that. If you're deploying it in an actual safety critical environment, the question is, does your code generator actually work? Congratulations, you just won a code generator in all environments, in all cases. There's multiple mitigations for that. Like, you can just go and say, I'm actually not going to check whether it works in all cases. I know the places where I'm using it, and I'm having someone reading the expanded source code, and I'm saying, in all of these cases where I'm using it, it's actually correct. There's all amounts of practices that you can deal around this. Problem is just, we've checked whether the compiler operates correctly. If you're putting plugins into the compiler, plugin is yours. Applied well, safety is actually close to good practice. And it gives a little bit of structure to quality assurance and helps us in critical thinking. So the ISO 26262 and the IA 61508 were good guidelines in the start, but also working with people who have actually applied them and found like good ways. And for example, the ISO 26262 says something about you should have tests and they should be traced to requirements. Does not say anything about a traceability matrix, specs, and how the spec should work and something like that. So practitioners that have actually put these things effectively into practice are really, really useful. Can be implemented with modern open source tools just fine. You don't need DAWs for tracking your requirements. And the other thing, and I think that's one thing that I really have to give the safety environment credit for, paying the people who made those tools remains good safety practice. Most of these people look at their supply chains and they're like, oh, maybe I want my compiler vendor to be around the next year. This is actually how people get in touch with you. And I think that's actually very compatible with open source, because the other side of open source after 2010 and 2020, where we scaled everything up, in the cloud space, everyone talks about, like, I have a successful project, but it's my hobby. My hobby is deployed somewhere in AWS Lambda or something like that. So I think there's a useful play between those things. So we do have to say open source actually works quite well in regulatory environments, and we never had any kind of problems with TÜV saying this tool is not fit for use because it's maintained by a couple of people down there in Austria or something, like Sfix. Still useful to make a case why you're using them. For us, it's been really useful to be able to modify those tools to our needs. For example, the requirements tracking does fundamentally rely on a small plugin in Sphinx. And having not to go through a vendor with a 2-year buying process and then saying, hey, by the way, can you do that fix or whatever? So we had a 2-year time frame as a very newcomer company. No one would build a feature for us if we wanted that. That's one of the strong points there. The critical variation, though, is important, and there's a reason why I've only mentioned 6 tools. Because we've only used these 6 tools. Maybe a small Python library somewhere. Otherwise, that process gets you stretched far too thin. If you're starting to modify 20 different tools and trying to rearrange them, it just won't work. Sum up, open source processes in safety are definitely usable. There's modern projects that have very big quality assurance processes. The Rust project is not the only one that's using this process. A lot of Linux Foundation projects are adopting those. And again, I would really love if there was actually like these environments would become closer together. One of the things being actually before going into compiler development, having done data center operations, the stakes in data centers are now, from a different angle, also incredibly high. So suddenly, like when I started doing that in 2008, 2010, there were a lot of things that worked as long as your boss didn't know. Not that kind of thing anymore. The largest formal verification group nowadays works at AWS and not at NASA. And there's a reason for that. The systems are getting so big and the damages, just the monetary damage is so high. Pretty sure the people from Bloomberg will agree that good software quality becomes a mandate for basically every environment. It's a niche, but it's a growing niche. But and for several reasons, a lot of companies nowadays do actually understand that liberal licensing is very useful for them and also compatible with everything that they built. The problem of illiberal licensing means I have a library supplier from over there and I have a library supplier from there. Are their licenses compatible? And our license says, this is the license for these pieces of code. We don't care about the things that are around, so we are compatible with everything else. If you need to have a conversation about open source in the supply chain, this has been something that we've experienced very hard. That 5 years ago, a lot of people did not have that kind of thinking. Nowadays, even classical engineering has an open source office and a lawyer who's an expert in this, and suddenly you can have that conversation. The biggest gap is that customers want safety and support service level agreements, and they want to understand how you're operating. And yeah, the other thing is usually documentation in these kinds of environments is not openly available. Openly available documentation allows products to refer to each other and refer to each other's assumptions, which is, in my opinion, a win. The other last big question, one thing that I heard very early on in this project is like, you're never going to certify a compiler on GitHub. You need to operate the infrastructure for yourself. That's a position where you should very early on call the assessor, because their answer was, who told you that? So assessors nowadays are also actually pretty modern and are aware of this. They will ask you, like their argument was actually, you're a 25-person company, don't operate a data center. There's people who have a certified data center, and probably the people at Microsoft are much better at security than you can ever be just by virtue of the amount of people they have. It's not a skill question, it's a capacity question. Straightforward and easy to follow processes are useful everywhere, and since I've engaged in the Rust project, I'm very happy that the build and release and testing process, once you grokked it, is actually pretty simple, and that makes it very easy. It's a lot of work to get there, and there's quite a few things that break when you actually start automating on the GitHub API and things like that, but simple processes are easy to vet where the breakage is. And we do actually rarely run into any platform limitations. If we do, there's usually workarounds. The biggest platform limitations are actually, do they support testing for hardware that we need? Is there a simulator available? So the biggest hardware limitation, platform limitation we basically run into is if we need to test on physical hardware. How do we get out of the data center to our physical hardware? And there the question is, where do we lock the hardware away? Much better question. And yep, coming back to the old thing, let's start with your automation early. It's actually quite useful to have it around from the beginning. And that's the end, short rush through everything we did. I hope it was useful to you. Happy to take any questions here or in the past. There's a question over there.